So today we are thrilled to welcome Professor Charlie Zender, who discovered his passion for scientific challenges, intellectual history, and to quote him, poorly conceived pranks during the 1981 summer science program in Ojai, California, after his junior year in high school. He received his bachelor in physics from Harvard in 1990, where he gave weekly sky tours at the Loomis Michael Observatory, sold Amiga computers, and worked in the high energy astrophysics division of the Smithsonian Astrophysical Observatory. And so astronomy sparked his continuing interest in atmospheric radiative transfer, and he taught math and physics for a year at the College of the Atlantic before entering the PhD program at UC Boulder, where he studied with Dr. Jeffrey Keel in the climate modeling session of NCAR. He became interested in aerosols in 1995 while traveling through India. Um, and after finishing his PhD in atmospheric science in 1996, he remained at NCAR for 3 more years as a postdoctoral researcher, first in the ASP program and then in the atmospheric chemistry division. He then joined the Earth System Science Department at UC Irvine in September of 1999. He collaborated with NCAR's Climate and Global Dynamic Division as an affiliate scientist from 2000 and 2006, and joined the French CNRS Laboratoire de Glaciologie et Géophysique de l'Environnement for a 1-year sabbatical in 2007. Today, he will discuss using the self-describing netCDF format to accelerate scientific workflows, noting that the netCDF format has been especially helpful in climate data analysis. And with that, thank you so much for accepting our invitation, and I look forward to your webinar.
Absolutely. Thank you for that prolonged introduction. It reminded me of the days when I had more time to spend on science. Thank you also for inviting all of the CLIVAR working group that are here. It's a real honor to be able to speak to other experts and researchers interested in climate data analysis and how we can move it forward. Before I go any further into the talk, I do want to verbally acknowledge collaborators, long-term collaborators, Henry Butowski, Ed Hartnett, formerly of Unidata and netCDF4 co-author, and now of NOAA, and Zylar Assay Davis from Los Alamos, as well as the dozens of people who have volunteered to test and port and package NCO along the way. When I was asked to give a presentation to this group, I thought, well, what could I have to add to the body of knowledge that you all already have amassed in terms of machine learning, in terms of AI, deep statistics, and what's in your charter isn't exactly where I spend most of my efforts, and yet we do align quite a bit in the use of a data format that's self-describing. And I think a lot of us might take that for granted these days, but it wasn't always that way. And so it occurred to me that I could give a presentation where I emphasize how important that capability of a self-describing data format here in netCDF is, how I've been able to exploit it to accelerate scientific workflows, and some directions for the future to accelerate scientific workflows by further exploits. So today we'll begin with a little bit of the history of where large-scale data analysis for climate was when I got started and involved with it, and then look at how the project that I've been leading for a long time, NCO, has leveraged the capabilities of self-describing formats in terms of 3 specific ways. One is a domain-specific language. Another is high-level workflows. And the third is my most recent interest, hobby, passion, and that's lossy and lossless compression. So without further ado, in the early 90s, when I began graduate school, climate data was stored in idiosyncratic formats that were often model and or data set specific. And these formats were developed by within a group and were often only understood by one or a few people in that group. The masters who kind of controlled how that data could be analyzed were the ones who formatted it. And it was accessible. It was typical for these data sets to be accessible through a monolithic tool. And here I illustrate that with the CCM processor, which was used to analyze the predecessor of the Community Earth System model data output in the early 1990s. And as you can see, this tool, the processor, was operating system specific, so the Unicos operating system. It was dataset specific. It only worked on CCM data. And yet, despite those constraints and its Fortran backend, it was very advanced for the time. And I'm really glad I didn't start graduate school earlier than the early 90s. Because they had just modernized and they had features like extensible data lists, what we would call today coordinate-based subsetting, random access to variables. And so my first stopping point here is to ask, what did we gain when we moved to self-describing dataset formats like netCDF that itself was released in the first version of its modern incarnation in 1992? And the most important characteristic that these formats, HDF and netCDF, and I'll just say netCDF from now on, provide is the ability to query the entire contents of the data set. So we'll come back to that later. And then some of the other aspects of these formats that we can take for granted and don't often think about are how portable they are. For example, netCDF can represent integers as big endian, little endian. It can represent single precision floating point data as 4 bytes or 8 bytes, as it was in the Unicos days. And all of that's hidden by the self-describing format. These are scalable formats that allow us to access small subsets of large data sets now efficiently without reading the entire data set. They're now appendable, meaning that you can either redo a run and add some data to an existing data set or derive something and store it with the existing data and not pay the penalty of rewriting the entire data set. These dataset libraries are single write, multiple read. So you can have a process writing at the same time as multiple readers are accessing it. And they're guaranteed to be 100% backwards compatible. So you can feel confident in archiving data that you won't lose a byte. So if you're not familiar with NCO, I'll describe what it is. It's a modular set of tools that together can be used to perform data analysis, scriptable or at the command line. It's also, and something that I prioritize during development, meant to keep graduate students and early researchers from having to reinvent the wheel and waste a lot of time doing that. More recently, it's become kind of a standard whipping boy or straw man for people to demonstrate how their methods are much faster, better. And I think most philosophically, though, what NCO is the first that I know of representation of entire files as manipulable units of data. And in Earth system modeling and observational analysis, we have thousands of files often, and we often want to do the same thing to each file. And so NCO, of course, allows you to do that. And that's a very powerful way of thinking about an entire data set containing multiple fields. And now with hierarchical data, multiple data sets in a single file. And so I have tended to think of data sets as the unit of a file of data granularity, with exceptions, because of course often we need to do certain things to certain fields. And so under that, guys, all of these 14 netCDF operators can work together, and yet they all have their own identities and personalities, and when combined, you can script or execute a very powerful workflow. So we're not going to talk about all of these, and this isn't supposed to be an advertisement for NCO. But what we'll talk about are aspects of NCO that demonstrate the power of self-describing data formats as represented by NCAP2, which has a domain-specific language embedded within it. And by these two scripts, NC-CLIMO and NC-REMAP, that are high-level workflows that prevent or that replace the need to rewrite commonly performed activities like generating climatologies or regridding. And so in the NCO, kind of skipped a slide there, so now we're on topic 2. And so in the NCO ecosystem, you can pare down this tool set to this level, where you have binary executables whose functionality is all encoded in a C library. All the math, weighted averaging, metadata manipulation, all performed in the yellow box, which itself relies on only one real external library, and that is the netCDF C library. That's where you can do quite a bit, but only locally and on your own machine. So there's so much more power that's unleashed by the self-describing format. For example, UDUnits is a software component that recognizes and transforms between physical units like time. So linking to UDUnits allows us to do coordinate-based subsetting based on different calendars, dates, ranges, things like that. And of course, we often want to work on subsets of fields within a file that share common naming conventions. So a regular expression library is very helpful. Still, though, that was all local data processing. And what self-describing formats do at the cost of only one metadata read for the file is provide the access through a protocol called the Data Access Protocol for clients to execute commands on remote data sets. So transparently access and compute statistics on subsets or entire remote data sets without the user really knowing anything but the URL, for example, of the remote data set. And if speed becomes an issue, as it always is, you can thread these data sets, and you can do that with really anything. So that's not a property of self-describing data sets so much as just a way of acceleration. But what the HDF folks did in about 2000 was replace HDF4 with HDF5. And HDF5 contains more powerful data set structures. It's hierarchical. It allows for user-defined types. It contains new types that the original netCDF API did not contain, like unsigned 8-bit ints and strings. And so now with just relinking to HDF, all netCDF programs gain that power, and the API has stayed simple and the same. As researchers, when we're analyzing the results of a numerical experiment, often we need a new function, a new procedure to kind of surgically get at the physical or chemical or biogeochemical response of our Earth system data to an experiment. And we need to craft these new statistical analyzers in a very detailed way. And so we rely on the full expressivity of fully parsable and interpretable languages to do that. And in NCO, that domain-specific language is encapsulated in the NCAP2 executable. So there's a whole parser and lexer provided by the Antler project to NCO. And we use that to wrap the hundreds of statistical and mathematical routines in the GNU scientific library. So everything from differentiation to special functions, Bessel functions, all of the high-powered math that you want domain experts to code the fastest way to do. You want your numerical recipes, we go to the GNU Scientific Library for those. Once you have this kind of full-featured ability to do research-level analysis of data sets locally and remotely, often you find yourself doing the same thing over and over again anyway. Even though it's research, you never, it's like cutting onions with cooking. You never stop cutting onions. So we've developed high-level workflow scripts to handle the generation of climatologies and regridding. And although we recently put in a regridding weight generator of our own into NCO, we're able to rely on externally provided weight generation software like ESMF, which has been widely used for 20 years, and Tempest Remap, which I know no more accurate weight generation software than Tempest that Paul Ulrich in this group authors. And of course, once you get something with this much power, people want to call it with their own preferred languages. And so we have a set of wrappers called PyNCO, and that completes the NCO ecosystem. So we'll move from that to discussing how we leverage the self-describing dataset format of netCDF into a very user-friendly, we think, domain-specific language in the NCAP2 operator. So this is a fully parsed language that recognizes conditionals, control flows, loops. It can print, can do math. You can add methods to it. It allows you to store your programs in external files and reads them in. And as I mentioned already, the the real nuts and bolts and nitty-gritty of high-level math are handled by the GNU Scientific Library. So if you want special functions or random number generators or interpolation, you can access GSL. And so what does the domain-specific language provide, and how is it that this is really leveraging anything? Well, consider the example of deriving fields from provided fields. And the classic example of that is computing a wind speed from model output or from reanalysis of the zonal and meridional component. If you execute this in NCAP2, you don't have to separately read in U and V and output wind. It's all handled for you because the domain-specific language is linked to the I/O constraints of netCDF, and it knows what you mean because that's how we wrote it, to be parsed as if you were dealing with netCDF datasets. And so everything on the left-hand side is automatically written to disk if you want it to be. And if you don't, you declare it as a RAM, what we call a RAM variable. And the RAM variables are not written to disk. And further, we can hopefully intelligently infer what you want the attributes of your derived variables to be. And so we're going to demonstrate that with a technique that we call left-hand casting, where the example I'm showing here is constructing a pressure field, a four-dimensional pressure field from a model that is using a hybrid vertical coordinate system like CAM or E3SM. And the hybrid vertical coordinate system, the input data sets will have varying ranks and sizes and dimensionality from scalars to three-dimensional variables. And the pressure field is going to be a four-dimensional variable. And this is the single line that derives that mid-level pressure field from all of these input variables present in the data set. And that single line will write the P, the four-dimensional output pressure, to the data set without you having to do any input or output statements. And moreover, we're going to propagate the attributes from the leftmost variable on the right-hand side into our derived variable. So we're reading all that from the self-describing dataset format, freeing up the researcher to worry about things like the like the meaning of their analysis rather than the nitty-gritty of the attribute writing and I/O handling. So once we have operators like this, as I said before, we got to cut our onions still. Often the most common use of NCO isn't necessarily in one-off console-based use, but in constant use in a research environment where we're iterating and developing models or iterating and accessing new observations from satellites. And when you want to do that, a typical human workflow becomes too expensive to get much done in a day if it takes more than an hour. So our goal has always been for these workflows to take less than about an hour. And our climatology generator, NC-Climo, has a few inputs that the user will provide, starting and ending years of your simulation or data set. Where's the raw data? Where do you want to put the climatology? And if you want to regrid it to a desired output grid and you have regridding weights, give it the map. Another oft-repeated workflow is generation of time series data from multivariable data sets. And this is the case with many MIPS that require time series as input to those MIPS, like CMIP6 or the Ice Sheet Intercomparison Project, or name your MIP. And so we have what we call a splitting capability. And the way that looks for invocation is you just give the operator, the climatology generator, a bag full of files. You pipe them in, tell them which variables you're interested in getting time series for the output, and there you go. Regridding. The Earth system models these days are using more and more unstructured grids, curvilinear grids, and non-rectilinear grids. And so regridding becomes almost mandatory before analyzing your data and for final plot production. And if you have a large set of files, our NC remap operator will take that set of files and apply the same set of regridding weights if they're all on the same input grid. Or if your collection of files are all on individual input grids, you can send that bag of files to NC remap and it will infer the input grid from each individual file and regrid it to your desired output map. In other words, generate regridding weights and apply those weights, and you can regrid a bag full of satellite level 2B swath data that way. When you're doing these intense time-consuming workflows, speed is an issue, and so parallelization is very important. We have three parallelization modes: a serial mode, which just handles one job step at a time; background mode, which is our default, which uses an entire node in a shared memory way, and you can, with any granularity you want, access the typical Unix fork and wait capabilities, hidden by the script, mind you, and run your climatology or regridding. Or if you have access to multiple nodes, we have this MPI mode that can do round-robin scheduling of your job steps across the available nodes. The way that looks in climatology generation is illustrated here. Think of the blue as being one node, and due to I/O bottlenecks on one node, it's not really helpful to do more than about 12 things at a time, and so our default is to, for the climatology generator, to handle all the Januaries on one core, all the Februaries on another core, and so on, up to all the Decembers. And this script will then go to a second stage when it has some regridding to do because it's done the monthly climatological means. And so we'll load balance the seasonal climos with the regridding of the monthly climos and do likewise when we compute annual climos from the seasons and are regridding the seasonal climos. So in MPI mode, that looks very similar, only instead of doing that all on one node, you can access up to 12 in this case nodes, and so this is how that looks. I've mentioned regridding a few times, and often people want to get it all done at one time, get their CLIMOs generated, get that regridding done. And so regridding is handled by OpenMP parallelization by NCO. And so what OpenMP can do is it can see how many variables you are in the data set that you want to regrid, and then assign, let's say you have 3 threads that you want to devote to regridding. It can just give every third variable to a core and proceed in a round-robin fashion that way. Or putting it all together, you can do node-level parallelism over the files with regridding handled by OpenMP within each file. So regridding threads over variables, and the nodes handle the file level parallelism. The way that looks when users invoke it, it's really just a one-line command. Remember, we're trying to make this as simple as possible, and we've boiled it down to about this level of complexity, which isn't too far from how the Department of Energy model creates its ESMF inputs for the CMIP 6 collection. An atmospheric model might produce all of its fields, and you might want to get 500 years of that into a climatological time series 500 years long, and so you would give it some options for compression up here in blue, for beginning and end years in red, and then take your bag of files and send it to the climatology generator. A completely different model, here the ocean model MPAS, looks very much the same in invocation. You have some variables that CMIP 6 MIP requires. You have some options for the size and shape of your data that might change. For example, if you're doing creating time series of 3D variables, you don't want to go over generally 100 gigabytes per time series segment, so you'll shrink the size of a segment, and maybe some model specific switches, and then you invoke it the same way. All right, so how do those splitters stack up against the software handled by our friends who are using the CESM ecosystem software? And they're splitting time series out from multivariable data sets with a program called PyReshaper. And these benchmarks were performed by Min Xu at Oak Ridge National Laboratory and show on the horizontal axis 5 different splitters or reshapers, and the throughput time. So small throughput time is good here. And what I was saying before about people more and more using NCO as a straw man or a whipping boy to show how much better their software is the left-hand bar, which shows kind of the old NCO before we had it all parallelized. And this is really all that many people ever need or use is the old NCO, and it's relatively slow at splitting things. But if you use the new NCO, as of 5 years ago, new in serial mode, yeah, you get a dramatic improvement in throughput for splitting and regridding. And if you use the background, the default parallelism, actually, it's much better. PyReshaper serial mode and PyReshaper MPI mode are shown here, and you can see that the best of each family are comparable. However, this is a selective benchmark, and so full disclosure, Here's how that looks on 2 generations of CPU architectures. So same kind of task. We have these 70 gigabyte files that we're splitting into single variable time series. And on the sort of traditional Intel generation chips that were present in the Edison supercomputer, you can see that NC Climo and Pyre Shaper uh, kind of fall out this way, depending on what your output data format part, the formatting of the output data partition is. NC Climo does quite well, about 2 or 3 times faster. But then on the Cori supercomputer, which uses Intel's latest CPU architecture, which is quite non-traditional, you can see that Pyre Shaper retains its alacrity, whereas NC Climo suffers a serious setback. And so we still have work to do in taking advantage of the latest generation of architectures. Which brings us to the final topic. My latest interest is compression. And compression includes here both internal, lossy, and lossless compression of a data set. So what we're working on is reducing data set size. Why? Because data sets consume a lot of power, and storage in particular, storage consumes about half of data center power. So data centers also have air conditioning and CPU intensive computations, but storage itself, spinning the disks, accounts for about 40% of that power and of any affiliated greenhouse gas emissions. And a final point to note is that we can store the data that we want to store, the scientifically meaningful portion of that data, with lossy compression. And all we're getting rid of is noise and random bits. And so that if we can do it fast enough so that the users don't really notice that they're using compression, we can save a lot of space and possibly a lot of greenhouse gas emissions. So let's see how that pans out. All of these compression capabilities take advantage of features that were built into HDF5, and netCDF4 takes advantage of those. And HDF5 can accept any user-defined filter. They call them filters, you might call them codecs, on data in those HDF5 data sets. The netCDF4 and HDF5 installations always provide checksum, shuffle, deflate filters. And so most people are familiar with deflate. It's the same thing that GNU zip and the zip library, the zlib library provides. That's the deflate Lempel-Ziv algorithm. And as of 2018, you could provide one other filter to a netCDF data set, and it would use that. As of 2020, we began a project called the Community Codec Repository that implements more modern filters than deflate, which is, remember, the kind of original lossless compression scheme that's been in use, heavy use, since the early 1990s. So now we have some lossy and lossless compressors that are in the CCR, the Community Codec Repository. And as of last month, actually, netCDF has finally allowed the multiple filter and chained filter aspects of codecs to be used, so we can now use those. And here's how the CCR exploits self-describing metadata to allow modern compressors to be used with netCDF and HDF5. Basically, it provides a hook. And so an Earth System Modeler can now use functions much like the deflate function that they already use and invoke other filters like Z-standard or the lossy bitgroom filter. As long as they have the CCR installed, the netCDF4 and HDF5 layers automatically figure out what filters were used before reading a data set, so the user doesn't have to do anything. And as long as the CCR and the filters are installed, which is just a configure, make, install, all of the use of the codecs is basically transparent. So those codecs that I mentioned, here's how they stack up in terms of compression ratio or size. And so smaller is better. We have a 1 gigabyte data set. This is the typical size of the low resolution Earth system model called EAM. So 1 gigabyte is what the size is if you don't compress it. If you use any of these three codecs, they're all Lempel-Ziv compressors. They all give about the same data set size with a compression level of 1. You can also add and now chain lossy compression. So you do lossy compression, then lossless compression. So that's 2 filters, 2 codecs to further reduce the size. And this lossy compression is retaining 3 significant decimal digits in every field, guaranteed, no matter what the value. We'll skip over this in the interest of time. This is how the lossy codec is doing it. We're pre-filtering the data before we send it to the lossless compressor. The lossy compressor, you tell it how many significant digits with NSD, so the number of significant digits. So look at what happens if we take basically a single precision version of pi and we start retaining successively smaller numbers of decimal significant digits until if we only retain 1 digit, you get the value 3 1/8 as an approximation of pi. So this is what the lossy compressor is doing. If you have NSD equals 3, this is your value of pi, 3.1406. So now we're going to look at throughput. Remember, our goal is to make it hard for the user to know they're using lossy and lossless compression. Here's the time. The leftmost bar is the read time of the uncompressed data. The middle bar is the write time using the indicated compression algorithm or algorithms. And the yellow time is the read time for reading the compressed data. So the little blue bars never change. That's all reading uncompressed data. And you can see that bzip takes a long time to write, this red middle bar. Bzip takes a long time to write, but we just saw it gives the best overall compression when combined with lossy compression. Unfortunately, it's just a little unacceptably long in writing. So we're going to zoom in now and get rid of the bzip compressor and compare Z standard with deflate. And here you see that not compressing your data and just writing it is about the same as compressing it with Z standard. Yeah, there's a 10 or 20% penalty here between the red bars. And then reading the compressed data may be a factor of 2 to 3. But see how much faster that is than the current state of the art, which is what CMIP6 uses, which is deflate. The write times are painful. The read times are kind of painful too. And not only that, for a little bit extra in write time, you can use lossy compression at the same time and get very good overall compression ratios. So we find you can get, with Z standard, writes about 10 times faster in the realm of not noticeable by the user relative to current deflate, relative to not compressing at all, and 10 times faster than the current compressor, reading about 3 times faster. And if you want to go further with lossy compression, you can. And so to conclude, you can leverage the metadata in these self-describing data formats so that the software I/O layers can automatically translate these compression codecs for you and leave the users, the researchers, free to focus on the science and yet store about half the data, so compressing it by a factor of 2, or accelerate their currently compressed data speeds using modern codecs and thus reduce power and greenhouse gas emissions. And so this is an aspect of green computing we're really excited about. And it's all enabled by self-describing dataset formats. Thanks a bunch for listening. I really appreciate it.
Thank you so much, Charlie. So we'll take the next 15 to 17 minutes for questions from the audience. So if you have a question from him, you can use the raise your hand button or type it into the chat box.
Hi, I'm Noah. Thanks a lot for the talk and for the tools. I just had a couple questions. First is this seems like the implied environment for a lot of these tools is the Linux shell. For most of my work, the implied environment's like a Python environment or some sort of cloud service provided runtime. So I'm just kind of wondering what your thoughts are on how specific your tools are to that specific environment or what kind of patterns work across environments.
Okay, great question. So I'll have this slide as kind of the background here. Yes, these tools were developed for a Unix shell environment. They work fine on Windows too, so it's all, you can do it at your workstation. And how does that translate for Python use? Well, we have Python wrappers. They're really just wrapping the executables, so you can import the NCO pylib and call these from within your Python scripts. And then as far as cloud computing environments, we don't offer any capability in that in NCO. However, HDF and netCDF both do, and so that's really a shortcoming of the netCDF toolkit in that we don't take advantage of that yet. And to be more concrete about what cloud capabilities netCDF and HDF and the self-describing data formats offer, of course, Python is basically written on top of the IO is written on top of HDF, so it's possible, of course. But let me mention that in this netCDF 4.8.0 release of last month, the netCDF layer finally exposes the ability to read and write Amazon Web Service data and anything in the ZAR format. So ZAR just recently became accessible right here at this critical boundary where the NCO library passes all of its IO through the netCDF library, and the netCDF library just exposed cloud storage in a meaningful way, last month. And so we have a proposal in with NASA right now. It's a revised proposal, so we had it in last year as well, to access ZAR transparently through NCO. And so all of the things that you just saw would be available on the cloud as well, if the proposal's funded and after a year or two of work, I should caveat.
Yeah, it'd be great to see some of the benchmarks you had at scale for those type of workflows, but in the cloud or using cloud storage as a backend.
Yeah, so one other thing, I agree, I've seen great results. I've seen great results from Xarray in the cloud on similar data flows. And so I have to confess that the environment that I'm most intimately involved with is the research and development environment where we're doing simulations and archiving to disk farms at supercomputer centers, and they don't stay on there very long. So we're not really doing a lot of Earth system grid data analysis or data analysis of observational data like MERA2 that has all been uploaded to the cloud. But we hope to with this ZAR capability.
Right. We have Paul, do you want to ask your question, and then we'll turn to the chat box to answer one of those questions.
Sure. So first off, thanks, Charlie, for all of the work you've done on NCO. It's been a lifesaver in many cases, and dramatically cut down on the amount of work that my students in particular have put into data analysis. With that said, I still find students spend an extraordinary amount of time just doing basically data curation, data management, downloading, putting things into the right format. Where do you see us heading into the future in order to reduce the amount of time spent on more technical tasks and thus enabling more time for science?
Well, Paul, I wish I had an answer for you that that was novel. So let me point out some implicit assumption in what you just said. We both agree that everyone spends too much time data wrangling. It's hard. There's metadata. The lack of one little piece of metadata can keep your workflow from working as expected. If you're not a domain expert in that area of, say, remote sensing and GIS, and you don't know what that one little thing should be, you're kind of dead in the water, and you're at the reliance of the masters who understand that. So let me couch that in the sense of many of us are doing research, and expecting it to be easy per se is perhaps unrealistic. And so let's not set too high a bar for how easy it's ever going to be to do research. My own thought has been that user friendliness is key. In other words, I think a lot can be gained from expressing the APIs in a language or a mode similar to that which a reasonable scientist might be expected to understand. And so I think things like are overlooked often, like regular expressions, like making your options multi-keyed. So you send the same value to any key of your option. And the key is what encapsulates the fact that I might call this option the dimension option or the DMN option or even the hyperslab option. All of those keys can be synonyms. So the use of synonyms and regular expressions to understand them helps to translate the user's intent to what the backend software understands and actually works with. So I think we really want to start getting what the UI, UX people, the user interface, user experience people call the human factors aspects into software development and design. So the user experience is what would a reasonable first-year grad student, early career researcher who hasn't been doing this a long time, expect this stuff to be called. A second prong, of course, is the adoption and exploitation of metadata that could be there, but isn't, or is there and isn't being exploited. And as a way of reifying that, I'll point to the CF, the Climate Forecast Conventions. So those have been inordinately helpful in helping data producers express their data in the same language, making sure that the data sets they provide are parsable by a broad array of tools, Python, Xarray, R, NCO, NCL, MATLAB. Many of these now have functions that actually understand metadata guidelines, conventions, as they're called, developed by CF. And we're still, I think, in the early stages of that. I don't really have a better way of doing it than continually hammering on user friendliness and adoption and exploitation of the self-describing metadata formats that CF has done such a good job at exploiting. And I'd be interested how you would answer your own question. If you think there's some low-hanging fruit, I'd love to hear about it.
Yeah, I could probably go on for a little bit myself, but I'll let others ask you questions.
Okay.
Thank you.
Mm-hmm.
All right, we have a question in the chat box from Brian Mapes. Do you have opinions about betters versus for the CDO suite from Hamburg?
I just mean how it compares, you know,
Okay.
and are there
Straightforward.
some things they do
Yeah.
better, some things, yeah.
Yeah, sure. Is that Brian?
Yeah, howdy.
Oh, hi, Brian. Long time no see.
Yeah.
Yeah. Okay. So, it's really a case by case. But there, it's a case by case basis. So CDO is great. They have taken a lot of things that NCO does okay or well at and made them even better. And there are things that NCO does better as well. I think they're a much larger operation with base funding, which, good for them. European Union, you guys know how to develop cohesive, long-term, self-sustaining research enterprises, and the U.S. could do better at that. So if you had a particular nut you wanted to crack with CDO, I would probably have a more specific opinion, Brian. What I'm trying to say is that it's a case by case basis, and NCO tries to do things in one line. CDO, like, well, a longer line maybe, and then there's things it can do that we can't. So I'm going to shrug and try and stay out of the name calling business.
Yeah.
But I'm again curious what the users like yourself think.
I kind of go back and forth, or I find an example, whichever example comes up quicker for me, I use it.
So do I. Yeah, I think you're getting at what we kind of tritely say, there's no one tool to rule them all and in the darkness bind them. There are going to be there's going to be an arsenal of tools, and one thing that NCO has going for it, and this is not necessarily important but can be, is the same thing. You run it the same way on your laptop when you're off the web as you do on a supercomputer that's highly connected to a petabyte scale disk farm. It's the same command. And so I really like having that wide dynamic range of applicability. And that's why I often call it middleware. And I think CDO, same thing. You can run it the same way on a laptop as you can on a supercomputer. So that's where I think those are strengths, because if you're like me, you have spotty internet sometimes.
I see a question or a comment in the chat box by Noah. Do you want to unmute yourself and
Oh, it's just a comment. People can see it if they want to. Basically, I mean, most places in the industry just pays people to process data if it's too messy for scientists to use. Like, there's people who are paid to do this. So it's, I'm not sure that it's possible to make it so user-friendly that it's zero effort without cost.
Oh, yeah, there, I finally got the chat up. Thank you. I can read your question, Noah. Yeah, that's how industry would treat it as a technical issue.
But I had a second question. Seems like to me where netCDF falls flat is kind of like when you have this problem of like 10,000 netCDF files, and what experiment do they come from, and cataloging these data. And that's where a system like tables and SQL really have a strength, is in coordinating lots of small pieces of data like that. And for netCDF, I'm just wondering if you see any kind of potentials to extend the netCDF model to kind of accommodate that kind of queries across many netCDF files.
Yeah, the netCDF developers love to say they are not a database format. So they try and stay away from adopting database technology. But the self-describing dataset format that they have written, so this library, is itself called, and were I from Unidata, I would have oriented a talk like this towards the higher level utilities that exploit the database-like characteristics when you get into tens of thousands of files. And those are things like threads, which, as you may know, is a server that, and like Hyrax, the DAP4 server, that when used in conjunction, are what NASA and the DACs use to expose their dataset holdings to the public. So the windows through which things like Earth Viewer from NASA and WebWinds and all of the quick look formats that drill deep into NASA DACs, they're all based on these front end engines that automatically scan and update netCDF and HDF files as far as the metadata they contain, and then massage it into a contiguous and user understandable format, so it will present you with the total spatial range and the total date range, and then you indicate what coordinates you want. So it's not my area of interest, these front end translators between the back end petascale farms and what the users drill into, but they exist, and I kind of have to defer to the threads and OpenDAP folks and Hyrax folks for those capabilities. But that's what you're looking at by and large when you're looking at these front ends to massive data farms.
All right, it is 4 o'clock right on the dot on my end, so I think we will conclude today's data science webinar. So thank you again so much, Charlie, for giving us the talk.
It was a pleasure. Bye, everyone.